So the title is Boundary Feedback Stabilization of Freeway Traffic Networks. And I will deal with input to state stability and control. And I will close my presentation with some open questions and some experiments that we have done with my colleagues in China, in Beijing. So thanks again for the organization of the online seminar. I'm very happy to have the opportunity to present this work. So this is the outline. So the outline is, first I will start with from very basic concepts on traffic control, and I will start with some discussion on modeling. And we will see that the key point and the most difficult part as a control designer is the design of a boundary control. And we will see that we have some perturbations. So this is not only due to the fact that we have a model that is quite difficult to tackle, but also the fact that there are by itself some perturbation applied in the dynamics. So input to state stability is very natural in our context. And this is why I would like to deal with a main result of this talk, which is a statement with sufficient condition on input to state property. And for that, I will use the Lyapunov method, and I will show you how to implement this sufficient condition numerically. So then I will deal with numerical experiments with real parameters. So it will be a complete simulator of one of the ring roads in Beijing. So this part has been done in collaboration with Li Guozhang and his team in Beijing University of Technology. And then I will conclude with some open questions. And you will see that the open questions are more numerous than the closed questions. Okay. So first, let us start with a very basic model. So this is a very classical model on traffic control. This is the so-called Horoskull-Zhang model. So here I would like to consider several lanes that are just in cascade. So I will consider several lanes, let us say capital N, cascade lanes. And I will first describe in the green line, the green equation, the conservation of mass. So conservation of mass of vehicle inside of a domain. So it is just a derivative of the partial derivative of the vehicle density is given by the flux, so by this quantity, which is just the product of the vehicle density times the average speed. So here we consider a macroscopic model. We do not consider vehicle by vehicle the dynamics of each individual vehicles, but we consider a macroscopic model with density description. Okay. So the first green equation is just the conservation of mass. So nothing surprising on that. It's just the vehicles are just conserved along the network of traffic. And then the second equation is just a transport equation. So transport equation of what? A transport equation of the velocity of vehicles, so which is Vg. So I forgot to say that the density on the vehicle depends on x and t. So x is the variable between 0 and the length of each lane. And also it depends on where you are in the network. So this is why there is a subscript j. Okay, so Vj is the velocity, average velocity of the vehicles, depending on the place and where you are on the lane and on the time t. And so there is a transport equation. So you see that this quantity is transport, with V is the velocity and P is the pressure. So pressure function is just a function of the density given by that. So A and gamma are just two constants. So you see that here there is a power, so that the dynamics is nonlinear. So it is nonlinear in the row function, but also it is quasi-linear in the transport equation. Why? Because the transport terms, the velocity in the transport depends on the velocity of the vehicles. So you see that this equation is just a transport equation. So this is the velocity of the transport, which is just a function of the state of Vj. Okay. So we have a transport equation, but in fact there is a relaxation term, and the relaxation term is given by this orange term, which is just a relaxation of this transport term. Okay, so the relaxation is just given by some fundamental map V rho, which is very classical. So it depends on the density minus the velocity and with a constant tau. So there is just okay. So the green line is just a transport. It is just it's just a conservation of mass of vehicles, of the conservation of number of vehicles, and here it is just a transport equation with some relaxation. Okay, with some facts, some relaxation due to this quantity, and all the other constants all the other values are constant except rho j and vj. Okay. And so, by the way, I would like to emphasize an excellent book written by Wang Wu and Miroslav Kristich, and it just appeared in this year. And so I have this book in my office. And there is many interesting modeling dynamic models inside of this book, and in particular, this model is very well described, better than I'm doing today. So here, this is a quasi-linear hyperbolic system. Why it is quasi-linear? Because it depends, the velocity depends on the state itself. And what I don't write the boundary conditions so far. I will write them in a few slides. But before doing that, I would like to write this dynamical system using particular coordinate. So more precisely, I will introduce the Riemann coordinate transformation, which is just a way to diagonalize the velocity matrix, which is in the middle. Okay, so the velocity matrix is just given by zj and this quantity. So here it is just, you can see that in these variables, it is just a velocity matrix. It's just given in diagonal form by zj and this quantity, where zj and omega j is just a very easy transformation of the previous dynamics. So that we have a linear system. So everything is linear except that we have a product between the diagonal velocity matrix with the space derivative of the state. And again, you have the relaxation term as a source term. You see on the right part of the dynamics. So by doing that, we just replace the previous nonlinear dynamics into a linear one, but with a product with a diagonal velocity matrix, and there is only this nonlinearity inside of the dynamics. But anyway, it remains a quasi-linear system, quasi-linear hyperbolic systems. So what about the velocity? Okay, so the first velocity is just given by zj. Zj is nothing more than the velocity, average velocity. Of course, the average velocity, there is a sign. Okay, we are dealing with freeways, so there is nobody which is driving backward. Okay, we just go from the beginning to the end of the freeway. So velocity is always positive. Okay, so zj is always positive. So there is no dot on this sign. So zj is positive, and this bracket is the second velocity, and this second velocity can be either positive or negative. This is just what I'm written there. So here I just linearize the previous dynamics around a given state, given constant and constant with respect to the time. Okay, it is an equilibrium, and also with respect to the x variable, which is the space variable. So I just linearize the previous dynamics. Also, it is very easy. It is straightforward, and I have just the same velocity as before. Okay, except that it is computed at this state w star and z star. Okay, so here I recognize both velocities. So the first one is always positive. Okay, if it is a physical model, it should be positive. And second one, we don't know. We don't know the sign of second velocity, can be either positive or negative. And in fact, the sign of that is very, very crucial. Why? Because it gives you the fact that it is either on a free regime or a congested regime. So here in this slide, I just write all the full dynamics by stacking all together all the lanes. So imagine that you have a network of segments of a freeway, and you just stack all together all the local state into a big vector, which is given by this psi. And I scale the space domain, and the scaling depends on is described by that, where x is just the local variable inside of a segment. Okay, you see? So by doing that, we have just a variable y, which is between 0 and 1 instead of having x between 0 and Lj, where Lj is the length of the health of the G's segment. Okay, so the full dynamics is written like that. So there is nothing magical behind that. It is just a linear system. Okay, and a linear system where the lambda j is just a matrix, okay, or just by stacking all pieces of diagonal matrices into a big diagonal matrix, which is given by this lambda matrix. And here it is a source term. Okay, what about the source term? The source term is just described by the linear function, which is just coming from this part. You see here there is a velocity. Here there is a velocity. Okay, you see. So it is a linear contribution. So this is given by this M matrix, and the B is just due to the fact that you have the reaction term. So it is something depending on the state, on the equilibrium state. So it is just a constant which is given by that. Okay. So to summarize, we have a system of balanced laws given in diagonal form with a source term given as an affine function, which is m times psi plus b, where b is a vector. Okay. So yes. So now the space variable is no more x, which is an individual position inside of the segment, but it is just between 0 and 1, which is just by scaling all segments into 0 and 1. And we have this classical diagram, which gives you discussion about the sign of the second velocity in each individual segment. So remember that in each individual segment, we have two velocities, one which is always positive, and second one which could be either positive or negative. So if it is positive, it just means that the velocity is larger than an expression of the density. It just means that the highway segment of the highway is in a free mode. So there is not so much vehicles around you. Okay, so we are just as you are free. And in congestion regime, this is when the velocity is prescribed by the pressure of the density of vehicles around you. So it just means that the velocity is smaller than some function of the density. So depending on the sign of the second velocity, you are either in the free flow or in the congestion regime. And this is very important for us to know if we are in the free regime or in the flow, in the congestion regime, because the boundary condition and the well-posedness and the control problems depend very closely to the modes that you are. So to be more specific, we will consider two types of controls. So since we have two velocities, one which is always positive and second one that could be either positive or negative, the first control is the same for any cases, either congestion or free mode. So the first control is just unwound metering. So unwound metering, it is given by this picture. It is just the uj here. So you just regulate, you just control the density of vehicles that are coming inside of this segment just by selecting some lights. Okay, so between green and red, you have a period, and you can control the period between green and red of the lights inside for vehicles that go inside of the freeway. And by doing that, you just regulate the density of vehicles that are coming in this segment. Okay. So this is the first type of control. This is the unbound mentoring. So it gives you the first boundary condition. It is just a boundary condition for this segment at this point equals 0, at x equals 0. And so you have one unbound mentoring there, another control there for this segment, etc., etc. Okay. So this, to be more specific, I will consider proportional control for this unbound metering. So it just means that I would like to find a condition on the feedback gain, kj. So of course it depends on the lane j's that you are considering, and it is just a function which is around typical value that is suitable for the equilibrium. Okay, so it is just a proportional control around your favorite normal regulation rate. Okay, so this is the first type of control. And the second type of control depends on if you are in free mode or in congestion mode. So if you are in free mode, you need to, so remember that if you are in free mode, you are just there is a double F. It's a typo. It should be one single F. Sorry, it should be free there. If you are in a free regime, it just means that you have two velocities that are positive. So in that case, you need two boundary conditions at x equals 0. So this is why we have this kind of control, which is so-called from downstream to the upstream. So you see, so this is from downstream, which is the value of the velocity at x equal 1, and you feed back this value to the value of the velocity at the beginning. So by doing that, you have just to control a variable speed limit, which is just at the beginning of the segment. Okay, and you control this variable speed limit at the beginning of the segment, depending on what happens at the end of the segment. Okay, so imagine that you have a boundary control that depends on the case if you are a free regime or on the congestion regime. And in the congestion regime, of course, so remember that we have, in that case, we have a negative velocity. So it just means that we need a boundary condition at x equal 1 at the end of the segment. So in that case, you just need to control the variable speed limit at the end of the segment, depending on what happens at the beginning of the segment. So it is a so-called from upstream to downstream feedback. So you have to feedback the upstream velocity to the downstream control. You see? So again, you have two proportional gains, KJ V here. Okay. You have one feedback gain for each segment. Oh, sorry. Okay. And depending on the case where you have either you have a free regime or congestion regime, you need to have the first case of feedback or the second case of the feedback. Okay. So now, so this is the picture for one segment. So what happens for a network of segments? For a network of segments, you may have many different cases. So let us just consider the case of two segments. So the case on two segments, you can either have free regime, okay, free for the first segment, free for the second one, or congestion for both, or free for the first one and congestion for the second one. And it is not very difficult to see that the case where you have the first in congestion regime and the second one in free regime, it is not very difficult to see that this case is not possible. Why? Because in fact, if you see what happens for the boundary condition, you will see that there is something which is not possible physically. So it is not possible to have congestion first and free at the end. Okay. So this is why we are considering only three cases: free, congestion, and free congestion mode for two segments. And now if you have n segments, okay, 1, 2, 3 up to n, you have to think about the cases where you have first free and then congestion. Okay. So now let us combine everything. So remember that we have already described the dynamics except the boundary condition. So in this slide, I would like to emphasize the boundary condition for the previous system on a network of traffic in an highway. But so by doing that, I consider the first capital M, which is just the number of free regimes. So just by reordering my equation, I can assume that it is the first variables, and I need to find some boundary condition depending on the number of positive velocity and the number of negative velocities. And for positive velocities, I need to introduce the quantity of vehicles that that appear in the beginning of the on the highway. If I come back to my picture here, it is just in the beginning of my network of segments. It is just the number of vehicles that go at the number of vehicles that go at the beginning of my freeway. Okay, so it gives you a function theta of time t, which is just a function, which is a vector. Okay, which is an uncertainty. We see some things that we will see as an uncertainty around a given value, and it is the number of vehicles, that the flow of vehicles that are in the entry of the network. So to summarize, I will have boundary conditions with feedbacks. Okay, feedbacks of the information on the number of vehicles and the density of vehicles that goes outside of the network. Feedback with the number of vehicles that go in plus some uncertainty. Okay, this is very natural for our application. And the control objective is to deal with two uncertainties. So remember that we have one uncertainty in the source term. Remember, it was the B vector due to the reaction term. It is an uncertainty because it is something that we cannot control. And we have another uncertainty, which is at the boundary. So we have two uncertainties at the boundary, as in the previous slide, and one in the source term and in the dynamics when I have written the dynamics. So, and the goal is not to stabilize. We cannot hope to stabilize to reach equilibrium. We can just solve an input to state stability property, and which is described precisely in this slide. So the objective is to prove or to analyze the stability and to analyze the input to state stability with respect to the model drift B and the disturbance theta. To be more specific, we would like to find a beta 1 function of class KL. So I'm sure that everyone knows what is a KL function for in the audience of this online seminar of input to state stability, and a class K function beta 2, so that we have this inequality. And this inequality, of course, it is a function of the state. So psi is just the vector of all information at time t, and we will deal with L2 stability. Okay, L2 stability, because this is our favorite norm that we will use for this presentation today. Okay, so this is a control objective. And the contribution, I forgot to say that it is a joint work with Ligo Zhang. Sorry, I forgot to emphasize that. This is a joint work with Ligo Zhang, Wang Wu, and Lu. And this is a IEEE control system technology paper that appeared last year. And in this paper, we have this main result, which is a set of sufficient conditions so that we have a solution of our control objective. So the control problem is the input to state stability, and we have two sufficient conditions to check to get a solution to this control problem. So this condition introduces some constant values, so mu, kappa 1 and kappa 2, and a diagonal positive definite matrix P, so that we have these two inequalities. So here I forgot to say that E of 2n is just a projection matrix on some coordinates. So we have this inequality, and the second inequality, it just here you recognize. So G here you recognize the boundary condition. Okay, the matrix in the boundary condition. Lambda is a matrix of positive velocities. And with norms with absolute values there, I just removing all sign, just considering only absolute values of all velocities. So this is my first inequality, and lambda bar is just the maximal eigenvalue of my diagonal of this matrix. And the second inequality depends on the source term. So the source term is given by the matrix capital M. Okay, and a choreographic P of Y is just this matrix. So it is just the diagonal matrix P multiplied by a diagonal. So a diagonal I multiply by exponential of Y, of mu minus Y plus 1. The first eigenvalues that are positive, and the second one I multiply by exponential of mu Y the second eigenvalues of P. So you see, and lambda max is just the maximal eigenvalue of this matrix that you obtain there. So here you have one inequality. So there is no y parameter. So this is just one parameter, one inequality. And here there is as many inequalities as there are y. Okay, so there is an infinite number of of inequalities to be satisfied, which is given by this equation. Okay. But anyway, under this assumption, we have that this system, the previous system, is input to state stability with the boundary conditions that I have described in presence of the uncertainty in the source term and in the certainty in the boundary condition. Okay, nice. Oh, IE are the projection matrix. Okay, I have written that here. Okay, that's great. So let me comment a few about that. So first, I would like to give you a very basic idea about the proof, and then I will comment on the statement, okay, to show you how to check that. Okay, the proof is nothing magical, very classical. I just introduced, following the work of Jean-Michel Coron, Georges Bastin, Miroslav Kricic, and many others great researchers. I introduced the quadratic Lyapunov function candidate with the weighting function given by the diagonal matrix P, scaled by the exponential of y or minus y depending on the sign. Okay, and just by considering this Lyapunov function candidate, I compute the Lyapunov time derivative, and after quite long and tedious computation, we can check that we have this inequality. Just means that the time derivative of the Lyapunov function candidate is smaller than minus nu v, where nu is positive and alpha is also positive, times this quantity. Okay, so this quantity, remember that b is a constant vector and theta of t is just the value of theta at time t. So we need a strong regularity on the theta function, and we need to take the infinity norm of the theta function there. And we can check that under the condition of this theorem, we have this condition, okay, the blue equation, okay. And after integrating by using a comparison lemma, we can. It is not so difficult to check that we have input to state stability in L2 norm. Why in L2 norm? Because this Lyapunov function is equivalent to the classical L2 norm in space. Okay. Okay. So let me comment now the sufficient condition. So the first sufficient condition is given by the Wade equation, and so the Wade equation. You remember that there is a J matrix. So the J matrix is the J boundary condition. So since we are all expert in control, it is not very. It is quite natural to see that this is a discrete time Lyapunov stability condition. You see, because there is a G transpose time G. Okay, so it is a discrete time stability condition. So it just this Wade condition is just what you will get if there is no dynamics inside of the domain. Okay, if there is just a transport, no dynamics inside of the domain, you will have a discrete time condition for the stability, which is given by that. Okay, this is nothing more than a generalization of what you know for discrete time system, and to analyze the impact of the boundary matrix condition J. So this is my first condition. And second one is just this inequality, and it is a continuous time stability. Why? Because it looks like a stability condition, Lyapunov stability condition for continuous time dynamics. So imagine that you have your transport equation with the source term given by M. Forget about the boundary condition. In that case, it just means that along the characteristics, following the Riemann coordinates, we have just the source term which gives you the dynamics. So the source term is your dynamics. So you have M transpose P plus PM as in only classical Lyapunov analysis for linear system or finite dimensional, less than 0. Okay, but there is a small modification due to that. So it is a continuous time stability condition, and here you see the impact of the source term M. Okay, so assuming both conditions, so discrete time dynamics and continuous time discrete time stability and continuous time stability, then you have input to state stability of the full dynamics given by the previous PD, partial differential equation. So I would like, okay, so this is a sketch of the proof. The precise proof is given by in the paper that I gave, that I cite in a few minutes ago. Okay, so I would like to comment on these conditions. So the first condition is a discrete time, the second one is a continuous time. So I would like to emphasize something that P was assumed to be diagonal positive definite. So it is very classical, in fact. It is not, it is false if you do not assume that it is diagonal positive matrix, except if you have a commutativity condition. In fact, there is an integration by parts that is that we have, for which we have to be careful, and taking P diagonal helps you to have this integration by parts working. But in fact, we don't need that P diagonal, we just need a commutativity condition. And this is very clear in a proposition of this paper with Antoine Girard and Emmanuel Vitran, on which, in particular, we discuss about relaxation of this discrete time condition and continuous side condition for hyperbolic system with source term. And we show that assuming that P is diagonal positive definite is great, but in fact, we don't need P diagonal. We just need a commutativity condition. So taking P diagonal helps you to ensure the commutativity condition, but we may have cases for which the commutativity condition does not require P to be diagonal, to be more specific. And the second point that I would like to emphasize that mu is never assumed to be positive. So in fact, again, there is the same paper with Antoine and Emmanuel. We discuss about that, and there is also a very nice proposition in the paper, in the book of Bastin and Coron, which is just behind me. And proposition 5.2 emphasize that as well. So in fact, mu does not need to be positive. Yes. There is a baby maybe asking a question. I don't know. So the mu does not need to be positive, and to be more specific, we just need these both conditions. So discrete time in red, continuous time in green, and there is a balance between stabilities coming from the discrete time dynamics and continuous time dynamics. And in fact, when there is no source term, so when there is no green equation, just this equation, mu has to be positive. So this is very classical in the for linear hyperbolic system without any source term. Mu, we impose mu to be positive, but in fact we don't need, if we have balance between both conditions, we don't need mu to be positive. We have just to be a little more careful, but we not need mu to be positive. So it helps us to relax the conditions, the classical conditions that we have. Okay, so P does not need to be diagonal, but it helps. Mu does not need to be positive. And the third point that I would like to emphasize is that remember that we have an infinite number of conditions to be satisfied for the green equation. The green equation is the continuous time stability condition, which is parameterized by y, and y is between 0 and 1. So in practice, I have to check that for 0, 0, 1, all points between 0 and 1, which is, of course, impossible in practice. But we can deal with relaxation, and since the P of y is just an exponential, either exponential of mu y or minus mu y, you can just relax this infinite number of conditions into several finite number of conditions, which give you conservative sufficient condition. Of course, we are losing something, but it is not so. It is quite natural in Lyapunov approach to have this kind of relaxation and this kind of conservativeness. And to be more specific, we can just embed the infinite number of inequalities to be checked by some finite number of conditions to be satisfied, and this is just using some polytopes approach. And again, this is a joint work with Pierre-Olivier Lamarre and Antoine Girard, where we introduce that for hyperbolic system. And this is very useful for application. So, and yeah, so by doing that, we get linear matrix inequalities, or with small nonlinearities that we can manage by line search on on a few scalar parameters, and we can couple this set of matrix inequalities to be checked with some optimization criterion. And so by how to do that? By recall that the K inequality is given by the blue equation. So the blue equation gives you the depend on the nu, which is positive, which is just the speed of convergence without any perturbation, and alpha is just the asymptotic gain in the input to state stability. So we can also try to optimize and try to find the optimal control under some constraint on the inputs, on the control inputs, and to find the best nu and the best alpha. Okay, and this is what you have done on simulations. So here it is just academic example, and then after you will see a more challenging example. So this is an academic example of two segments of a freeway. So we have the first two. We have four segments. I'm sorry, I made a mistake. There is four segments, and the first two ones are in the free mode, and the last two ones are in congestion regime. And here you can see the velocity density, and here it is the time. So initially, and you have some perturbations, okay? And initially you have this state, and the velocity density converges to the equilibrium if the perturbation is not sufficiently large. Okay, you see that the effect of the perturbation is vanishing. Okay, there is a fading memory property of the disturbance on the solution. It's the same for the speed, vehicle speed, and here it is the time, and here it is the y variable between 0 and it is the x variable between 0 and the length of each segment. Okay, so this is just an academic example, and a more challenging example has been done by my colleagues in Beijing, where they have a very nice simulator software, which is just describing the dynamics of a portion of the fourth ring road in Beijing. So there is they are using the macroscopic model of Roscoe-Zhang to control to design the control, and we can have this with this software a microscopic view. Okay, so we can have all levels between macroscopic control, microscopic design approach, with microscopic description of vehicles on this software. And this software has been calibrated on this section of the road in Beijing, and this is the result. So here you can check that there is a 16 portion of the ring road with different lengths. So the length can be between 350 meters and 1,000 meters, and here it is the average density without any control. So without any control, it is in green, and with control, it is in blue. So you see that you do not converge to zero. There is no stability, no convergence, no attractivity towards the equilibrium, your favorite red lines. I hope that you can see. But you are closer, you are in the neighborhood of the equilibrium, and you are closer to the equilibrium in a smaller neighborhood with the control than without any control. So this is something that appears on the average density, and we have similar results for the average speed on each portion of the 16 portions of the road. Okay, so this is just an application of what we have done, where we control and we prove and we design. I should say we design boundary controls for this software, so that we are property input to state property of the density and the speed. And in fact, what is very good is that we can also estimate the travel times. Of course, the travel times is just the time it is related to a description in the microscopic level. So it is just the time that you need to travel from the beginning of this segment to the end of this one, or on the other way. I'm not sure. And by estimating that, we can check that the travel time is smaller with control than without any control. Okay, so it just means that this is an added value of our design, that we are also good. It has also a good impact on the travel times, which is an added value which is not on purpose. Okay. So this is the end of my contribution of today. I would like to deal with more general and different problems. And so far you have seen a result on the linear problem. You see, so this is input to state stability of the linear model on traffic flow. But if you want to look on what happens for the input to state stability of the quasi-linear system, this is something done in a work with Li Guozhang and Lina Guan, but so far it has not been done in the same context. To be more precise, we have dealt with input to state stability of the quasi-linear system by using a local approach. And we have done that with multi-class vehicles dynamics. So multi-class vehicle dynamics is something that has been also introduced very well in the book of Yu and Miroslav Kristich. And so this is when you have to deal with the dynamics coming from cars or from trucks. And of course, the pressure of a truck is different than the pressure of a bicycle. Okay, so to be more specific, you have some models of the variation of the Horowitz-Kolzang model given by the occupancy area, and the occupancy area depends on the row, the density, that could be either from trucks or from small cars or small bicycles. And the reduction term depends also on the area occupancy function. So this is just a variation of the Horowitz-Kolzang property, and for which we have dealt with input to state stability or local input to state stability for the quasi-linear systems. Okay, so for the quasi-linear system, how to deal with input to state stability by first linearize and then deduce a local result in appropriate norm. So this is a paper that is currently under review with Lina Guan and Li Guozhang. And there are, as always with Horowitz-Kolzang traffic, there are some perturbations. And another problem that I would like to deal is an observer design. So far in the previous slide, we deal with stabilization, and so far we have dealt with proportional control. And proportional control, if we assume that we have a non-collocated boundary sensors. But what happens if we need, in addition, an observer, or if you want to observe the system, if you want to use the model to estimate the number of vehicles inside of a network, okay, just by measuring what happens at some boundary, at some points. And this is a joint work with, and again, so the observer dynamics, there is no hope to have a stability because there are always some perturbations. So this is just an observer design in input to state stability context. And this is a joint work with Rafael Vasquez and the same authors. And there is a very nice chapter 4 of the same book, and a very nice work of Jean Oriol and Federico Brubesca-Argomedo dealing with observer design by using backstepping, or by using backstepping on the Horowitz-Kolzang, or by using backstepping on ODE, PDE, ODE system, for which we have linear hyperbolic system. Okay, so everything is linear there, but there are more dynamics than just one PDE. There are also ODE at the boundary, and these authors were able to design observers, and it could be great to look on the input to state stability of the aerodynamics of these papers, of this work, in case of we have dynamics, perturbation, sorry, inside of the dynamics or at the boundary conditions. Okay. And the last slide of today is this one. So assume that you have an observer and you have a state feedback law. A very natural question is to close loop, okay, to make the closed loop. So to close the loop with the observer, and closing the loop between backstepping control and observer for quasi-linear system is still not known, not done in the case of perturbation. And I would like to give you four references on that. So the first one is about a quasi-linear hyperbolic system, but 2 by 2. Okay. In this very nice paper of Raphaël Vasquez, Jean-Michel Coron, Miroslav, and Georges Bastin, they succeed to combine observer with a state feedback law for quasi-linear hyperbolic system. So it is a very nice result. And then for 1D inhomogeneous quasi-linear hyperbolic systems, this approach has been generalized in this paper. And you can also consider this work where you have a similar result for 2 by 2 quasi-linear system. And again, this approach has been described in very elegant way in chapter 10 of this book. So, but closing the loop between observer and state feedback law there are already very interesting works, but it is still there are many open questions on that. So the first one is, what about the perturb case? And I'm not sure that we have dealt with input to state stabilization by means of output feedback laws. And I'm not sure that I have seen so far application to traffic control for N by N case. So this chapter 10 deal with traffic control, but only for a cascade of 2 segments, not for a cascade of more than 2 segments. Probably it could be adapted to that case, but it is so far still an open question if I'm right. Okay, so that's the end of my talk. So I would like to thank you for your attention of this presentation. I would like to also to thank my sponsor, and I'm ready to answer to your question if any. Thanks again, Patrick and André, for organization of this seminar.